A student investigates reactions of aromatic compounds. The student first carries out the reaction shown below. So this is the reaction of quinol, which is an aromatic compound, with 2-methyl-2-chloropropane, a halogen carrier of iron trichloride, and we're producing this substituted compound E. So we've substituted one of the hydrogens on quinol with our compound here, and we're also producing some HCl overall. And this reaction, where we're adding on a carbon-based compound to our aromatic compound, is one of our Friedel-Crafts reactions, just for reference. And we are told that the student contains a very low yield of this compound E here. And we are told that the student obtains a much higher yield of a different organic product with a molecular formula of C14H22O2. And we need to suggest an identity for this organic product, and we need to draw its structure below. So first, let's work out the molecular formula of our compound E, so then we can see how this new organic product is different to compound E. So compound E contains carbon, hydrogen, and oxygen only. So let's go through and work out the molecular formula for that. So for carbons, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 carbons there. For hydrogens, we've got 1, 2, 3, 4, 5, and then we can add on 9 overall from this group over here. So overall we've got 14 hydrogens and we've got 2 oxygens there overall. So we can see that the main difference between the molecular formula of compound E and our organic product here is going to be a difference between the carbons and the hydrogens. And specifically, we've got a difference of 4 carbons and we've got a difference of 8 hydrogens. And this is going to match up with adding on another unit of our 2-methyl-2-chloropropane where we substitute it on, so we end up with just the methyl propane added on overall. So this could be substituted on. So we're going to get a double substitution overall. So let's start by drawing out this organic product. So there are a couple different options for our new compound. So we could either have this substitution here, like so, or if we draw out the same compound again, so we've got our quinol base, we've got our group 1 like here, we could substitute it up in this position overall. And you might be able to draw some other configurations, but they all end up rotating or flipping back to these 2 configurations overall. So the mark is for drawing one of these structures. The student is told by a friend that the iron trichloride catalyst is not needed because quinol is more reactive than benzene overall. And we need to explain why the student's friend is correct. And we can draw a diagram to support our answer if we want to. So here is our structure of the quinol, where we've got these 2 hydroxy groups directly bonded onto that benzene ring. So what I'm going to do is I'm going to start by drawing out the benzene ring in a slightly flatter configuration. Now I'm just going to draw the outside carbon atoms here, and what I'm going to add on now are the p orbitals. And I'm going to use this to show the overlap above and below the ring of the p orbitals. And this is where the spare electron per carbon is held. We get this overlap above and below the ring. And this is going to cause this ring of pi delocalization here. Now, what happens if we add the 2 oxygen groups on with the quinol? So I'm going to add them either side, like so. And I didn't draw out the hydrogens for the original benzene because it's a skeletal formula, but I've drawn in the whole hydroxy group here for the quinol. And what we know about oxygen is that this atom of oxygen within this hydroxy group bonded directly onto the ring has got 2 bonding pairs, but it's in group 6, so it's got 6 outer shell electrons. Therefore, if it's used 2 for bonding, it's also got 2 lone pairs. And one of these lone pairs is going to be held in a p orbital that is in the same plane as the p orbitals from that benzene ring. Therefore, we're going to get some partial delocalization into that ring. So we're adding more electron density into the ring overall. So let's write these bits down to start off. So we've got lone pairs of electrons on the oxygen, and these are from the OH and quinol, and these are going to partially delocalize into the ring overall. So this is adding electron density into the ring, therefore making it more reactive overall. So no catalyst is needed. Therefore, this makes the quinol more susceptible to attack from an electrophile. So we've got more electron density in the ring, therefore we're going to be more susceptible to an attack from a positively charged electrophile or a slightly positively charged electrophile, so we can induce dipoles easier overall. And for this question, there's 1 mark for mentioning the lone pair of electrons on the oxygen, which we've also shown here in our diagram. There's 1 mark for mentioning that these are partially delocalized into the ring. Again, we've shown this in our diagram above. And the final mark is for mentioning that this makes the quinol more susceptible to attack from an electrophile overall. 4-nitrobenzoic acid is an important compound in chemical synthesis. The flowchart below shows a synthesis involving our 4-nitrobenzoic acid. So we've got our 4-nitrobenzoic acid here, and we've got a first step leading to compound F, then a second step leading to a product. And for the first part, we need to state suitable reactants and conditions for step 1, so that's this first step here. So let's look at the differences between our 4-nitrobenzoic acid and our compound F. So we can see that on compound F, we've got an ester group overall. Therefore, this reaction for step 1 is an esterification reaction overall. And for this esterification reaction, we're going to need some concentrated sulfuric acid, and that's acting as both a catalyst and a dehydrating agent. And we're going to need an alcohol in order to react with this carboxylic acid group, and the alcohol we need is derived from this section, so we've got 2 carbons, therefore we're going to need ethanol, which has got the structural formula CH3CH2OH overall. And in order to get the mark for this question, you need to list both the sulfuric acid and the ethanol in order to get that 1 mark overall. So you need both of these for the mark for this part. And we are told that in step 2, the nitro group in compound F is reduced by tin and concentrated hydrochloric acid. And for this question, we need to write an equation for this reduction of compound F, making sure that we show the structures of any organic compounds which are involved here. We've got our reduction reagents here, and this NO2 group is going to be reduced to an NH2 overall. So we're making an aromatic amine in this question. So let's start off our equation. So we'll start off by drawing out our compound F for our first part of the equation overall. It's shown like so. So we've got our ester and then we've got our nitro group. And we're forming the aromatic amine version. So our NO2 is going to turn into an NH2 overall. So that's shown here. And we can represent these reduction agents by using a square brackets with a hydrogen. And this is the key reactant from these reducing agents overall. And we're going to produce another product as well, because we're going to need a second product which contains some of this oxygen, which we've used to reduce our compound to the NH2. And it's got to be a small molecule that's produced here. And for this reaction, we produce water overall. So now we just need to balance this all up. So if we're producing water and we've lost the 2 oxygens from here, we're going to need to put a big 2 in front of our water in order to have the same number of oxygens from these parts here. We don't need to worry about these oxygens because they've stayed the same throughout, so we don't need to include them in our counting for this question. So now let's count up how many hydrogens we've got on the right-hand side. So we've got 4 from the water and 2 from the amine. Therefore, we need 6 molar equivalents of our reducing agent overall for this equation. So now we've drawn out our organic structures and we've balanced the equation. So 1 mark is for drawing out both of the structures. So you need to have both of these organic structures in order to get that 1 mark. And the second mark is for balancing the equation correctly.